Hi. Okay, I'm going to start with 8.2 now, which is forces on charges in magnetic fields. So I mentioned that in 1820, Oersted found that a current in a wire deflected a nearby compass. Ampere took this further and found that actually if we had currents in two nearby wires, they exerted a force on each other. And so what that means is that moving charges will experience a force in a magnetic field. And this force is given by this equation here. Fb, the magnetic force in newtons, equals QV cross B. So this is a cross product. We have Q, which is the charge in coulombs. V is the velocity of the charge in meters per second. And B is the magnetic field strength. The unit for the magnetic field strength is Tesla, and 1 Tesla is 1 kilogram per ampere second squared. So this is the unit of magnetic field strength or magnetic flux density. Okay, so this is a cross product, which means that it produces a third vector perpendicular to both the original two vectors. So the magnetic force will always be perpendicular to both the velocity of the charge and the magnetic field. This also means that since it's a cross product and the cross product of parallel vectors is 0, that the magnetic field does not exert a force on the charge if it's parallel to the direction of the charge. So the charge has to be moving and it has to have a component of its velocity that's perpendicular to the magnetic field in order to experience a force. So you can calculate this cross product two ways, either using the vector definition of the cross product, which will give you a vector with a direction, or by using the magnitude. So the magnitude is Fb equals Q V B sine theta. And if we write it like that, then theta is the angle between the velocity and the magnetic field. Angle between V and B. And if you're using this method, then we need to use the right-hand rule to determine the direction of the force on the moving charge. So it's the same right-hand rule that you would use for many applications of the cross product. And I'll describe it here. First of all, if you see these symbols, this X here means into the page, and then the dot means out of the page. Okay, so for the example here, I've chosen the magnetic field to be going out of the page, and we have a positive charge that's moving in the electric field. So the rule I'll explain will give you the force on positive charges moving in an external magnetic field. Okay, so our magnetic field out of the page, positive charge going towards this direction for velocity. And now I'm going to turn my hand so that I can curl my fingers in the direction of the magnetic field. So I have my fingers in the direction of the velocity, but I'll turn them so that I can curl them out of the page. And when I do that, because that's my magnetic field direction, the force is down on that positive charge. So the instructions were place your fingers in the direction of the velocity of the moving charge. You may have to turn your hand so that you can curl them for the next step. Then you're going to curl your fingers in the direction towards the magnetic field. So you're turning the velocity into the magnetic field vector, and then the direction your thumb naturally points is the direction of the magnetic field. And we'll look at some examples in just a second. Okay, so for example 1, determine the direction of the magnetic force in each of these following cases. We can use the right-hand rule to give us the direction of the force on a positive charge. If the charge is negative, the direction of the magnetic force on that charge is exactly opposite to the direction that it would be on a positive charge. So we'll use the right-hand rule and then multiply it by -1 to find the direction if it's a negative charge. Okay, so let's start on A. So our magnetic field here is what's into the page, and then the velocity of the charge is directed to the right for this positive charge. So I'm going to place my hand in the direction of the charge, curl my fingers into the page toward the magnetic field, and I get this direction of upwards for the magnetic force. Now I'll keep going. So moving on to B, we have our Negative charge, I'll still use my right hand, and I'm going to put my fingers in the direction of that negative charge, and then I'll move my hand so I can curl my fingers up towards the magnetic field, and notice I get into the page here. So I need to flip that because it's negative. So we have out of the page for a magnetic force. Okay, and let's look here. In this one, you'll have a problem if you go to use the right hand rule. And the reason is that these are parallel. So what happens is there's no magnetic force, right? We would have sine of 0, which gives us a magnetic force of 0 because the charges are moving. Actually, the charge is anti-parallel to the electric field. So we would get sine of 180, and still that would give us 0 here. Okay, so D now, I'm going to place my fingers in the direction here of the moving charge, which is this positive charge here, curl them towards the magnetic field. So I'm turning this velocity vector into the magnetic field, and my thumb goes into the page. So this one's into the page. All right, so example 2, consider an electron near Earth's equator. Which way does it deflect if its velocity is directed? First case we have down, so I've drawn an image just to help. We can imagine that north is into the page. You could choose any dimension that helps you just to orient the rest of the directions to give an answer. So if I pick north and we have the electron going down, I'm going to put my fingers in the direction down for that velocity, and then curl them into the page. And then I get this direction that would be east. So I need to flip it because it's an electron, and my force is going to be to the west for the answer to A. All right, looking at B, this is north, and our magnetic field is north. So we know now that that is parallel or anti-parallel, and we still get no magnetic force. The charge is not deflected in that case. Okay, so for C, now we have the electron, stand over here, going to the west, and the magnetic field still into the page. So if I put my fingers in the direction of the charge, move them into the page, I have down, but I have to flip it because it's a negative charge, so that will be up. Okay, so now let's go on to D for east. Now my electron's moving to the east. I turn my hand into the page. I get up, but I have to flip it to down because of the charge being negative. Okay, so for the last example here, example 3, a proton is moving in the positive x direction at 8 times 10 to the 6 meters per second, and a uniform magnetic field of 0.025 Tesla is switched on in a direction 60 degrees above the positive x-axis in the xy plane. Determine the direction of the magnetic force. So the simplest way is to use the magnitude definition of the cross product and then use the right hand rule. First, to get the direction, if we draw the magnetic field here, place my fingers over here in the direction of that velocity, and then curl them up towards the magnetic field. My thumb is out of the page. So we can already see that it should be out of the page, and that would be in the positive x direction, positive z direction, based on how our coordinate system is set up. So out of the page there. And to get the magnitude, we have QVB sine theta. So that Q charges an electron, just the magnitude here. So no sign, 8 times 10 to the 6 meters per second, and then the magnetic field strength, sine 60, the angle between V and B. And that gives me 2.77 times 10 to the negative 14 newtons. Okay, so that's probably the way I would do it, but just to show you that we can also do that using the cross product, I think part C actually had asked you to repeat using the cross product. So to do that, we need our vectors in component unit vector form. So first find the sine and cosine components of x and y components of the magnetic field, and it's just an x component for the velocity here. There. And I'll just take you over to show you I've worked this out over here. All right, so here I have the cross product definition up at the top. So to do that, I'm using a vector v cross b, and then I have my vector set up, I hat, j hat, k hat, vx, vy, vz, and then bx, by, bz, so placing them as we would for the cross product and filling in the components. And then here, when we look at doing this, you can use any method for the cross product. You have a long formula to plug in if you want to, or I suggested the kind of covering method. So I would cover the first row in the first column, and that's times I hat. If I do that, I have zeros. I get 0 times 0. And then j, I cover the first row and the second column, and I get this vx times 0, and then also bx times 0 when we cross multiply. And then k, covering this last column, it's the only one that's non-zero. So we multiply down across, 8 times 10 to the 6 times 0.0217. And this way we get a 0. So we would subtract this product, but it's 0. Okay, so that gives me v cross b, and then in the last step we just multiply it by q. So I have that times q there, and then giving me a final result of 2.78, so very similar, times 10 to the negative 14 newtons. And this time it gives us the direction, so we can see that that is in the positive k hat direction. I went over the cross product in Module 1, so you can refer back to that if you want to see how to do the vector cross product. Okay, that's all for 8.2.